You just thought things were getting crazy in my last video where I was putting one sub behind the other, but today we're going to take 3 subs and turn the middle one around. So it's going to be facing backwards. And so you can have even more A2s thinking you are crazy by putting your subs in weird spots. So this is the gradient inverted stack cardioid subarray, okay? And we're just going to call it the inverted configuration for short. So we're going to walk through step by step how to put it together, how to verify it in the field, see results I got from putting it together in a local shop. One of the main tools we're going to be using today is my audio math survival spreadsheet that is available at producedbymkc.com/audio toolkit, or it is at the link below. There's a ton of great stuff in that toolkit, but as the main tool we're going to be using today, it is all the nerdy calculations you need to put a wonderful sounding rig together. So without further ado, let's jump into what's to come with our video today with our gradient inverted cardioid subarray. So our roadmap today is first discussing what in the world is this array anyway? Why is it different from other subarrays, and what are the pros and cons of putting it together? Second, we're going to be talking through step by step how to deploy it. So not quite all the super science behind it, but if you were just to put together a step-by-step manual of putting it together in the field, this is what it would look like. And then we're going to talk about how and when not to deploy it, because you need a very specific set of circumstances to make it a good choice for your show. And then we're going to jump into the nerdy stuff, and I'm going to show you how and why it works, why we're able to get a bunch of cancellation in the rear of the array, which means it's not coming on your stage, and we get extra summation in the front, which means we have more firepower in front of array, which is great. Then we're going to look at real results in Smart and from what I captured when deploying this array in a shop, so you can see in the real world how much cancellation and summation you're actually going to get and what the pattern is going to look like. Then we'll wrap up and talk about how you can practice this ahead of time. When the riggers are waiting on you and you're loading in and it's short on time already is not when you're supposed to be figuring out where to put your microphones. So knowing ahead of time, having a clear roadmap ahead of you is what's necessary here. So we'll talk about how to practice that. But before we jump in, I want to say a big thanks to VOD 3 Event Production. They're in Lowell, Arkansas, and they do stuff all over the country. And I'm thankful to be a part of their freelance roster, and they let me come in and make some noise in the shop, and it was really helpful to get this data. So thanks again to Cameron and the team. So let's jump into what and why is a gradient inverted cardioid subarray. So as the name suggests in this array, we are getting a cardioid coverage pattern. This is the same as a microphone in reverse. It is capturing things in a cardioid pattern. So it's going to be listening and most sensitive to that upside down heart shape pattern. So we can achieve this by displacing the 2 front and then 1 rear drivers, adding some delay to the center one, and doing a polarity inversion. And that's the formula we're going to step through a little bit later, but it is through that processing we're able to achieve that type of pattern. And so just like a cardioid microphone is really great at rejecting sound from a monitor in the rear, and that's where you want to point the null of a microphone, we can do the same with the stage. So we're not getting the leakage from the rear of a sub coming right back onto the stage and causing your kick drum to feedback. We can direct that low into the audience and take it away from the stage and the back wall, so we get ultimately a more coherent and tighter sound. So it's the same as taking an Omni microphone and flipping it to a cardioid pattern, much like on a C414. There are even some variations of physical displacement when doing this inverted pattern. So you can put some in a stack, like 3 on one another, or you can do it in a line like I did, but we can do that more in a later advanced techniques video. So here are the pros and cons of using this particular array. So our first pro, like I said, is the less low end leakage on stage. We have a lot of the energy moving forward out to the audience, and we have it canceling in the rear. So it's going to be a lot less just rumble happening. There are going to be less low end reflections off the back wall, so you're having less low end swimming around in your venue. It's going to be a smooth, even coverage from the center if you're doing a center array versus a couple of space left, right. I know sometimes it's unavoidable to have to split up your subs because you can't put them in the middle, but I definitely prefer a center sub array, either flown in the center as top priority. If I can't do that, a center down front. So this array is also great at covering wide rooms from the center. So most main speakers aren't going to be wider than 100, 110 degrees, which is still a pretty wide pattern, but this cardioid array gets even wider. You might argue that yes, a single sub is 360 degrees, and I get that, but I like being able to focus energy in this direction with the cardioid array, but it's still nice and wide. But you can narrow it up by doing a spaced array of sorts, and we could talk about that a little bit later on. It's pretty easy to simply stack more subs, so you can still get more SPL just by stacking them up vertically. You can just still do this array. And lastly, your monitor engineer is going to be happy with you because you have a lot less low end pummeling them in the chest when they're trying to get a good feel for the kick drum in their ears. Yeah, this one is also really easy to fly and stack. This is the most common cardioid sub configuration you'll see when stuff is in the air. So moving on to the cons, it takes an odd number of enclosures to deploy this. So if it's front, rear, front, that's 3. And for whatever reason, production likes to do stuff like Noah's Ark and have everything in pairs. And so you may not need all the SPL 4 subs has to offer, and you can definitely do it with 3. But sometimes you might be leaving out gear that took up room on the truck if you're doing an odd number. It's not always an odd numbered setup because you can do front, rear, front, and then front, rear, front of doing a 6-element array. And so that is even, but if you're doing a smaller array like this, you could leave a sub out. It requires additional processing outputs to make this happen. It just needs 2 separate drive channels. One's the clean send to the sub, no delay, no polarity inversion, but the second channel to only the rear sub is gonna need delay and polarity inversion on that. So you either need a separate DSP or need to eat up an output on your console to take care of that. And it also takes up more lateral real estate. So a single sub spaced or 2 subs spaced left and right can get out of the way more easily than 3 all right together. If for some reason you needed some security fencing down front or had to place a front fill really specifically. So just know that it's going to take up that amount of real estate. I was using KW181s from QSC, and those are just single 18s, but this array can get really long if you're using double 18 enclosures. So when should you not deploy this array? Definitely don't do it in front of a hard stage front, a concrete or metal stage front, because it needs clearance for that wave to come back and cancel. If it's bouncing right back, it's going to screw up that cancellation. And so if you're in front of a hard wall or a hard stage front, don't deploy this array. And if the artist really, really wants to feel the low end on the stage and feel it in their chest, this is going to make it feel rather anemic on stage, which is good for you since you're not getting it coming back in your microphones. But if your artist really wants to feel that bump, I would not deploy this array. So here are the 5 steps to deploying this array. We're going to talk about a little bit later all the nerdy stuff and how and why it's working, but this, if you're just to follow step by step, this is how you would deploy it. You're going to place 3 of them in a row. The outer 2 are going to be facing forward out to your audience. The middle one's going to be facing to the rear. And you're going to have about a fist size spacing between them. Merlin Van Veen has a brilliant article on why this helps with cancellation in the rear. I'm not going to get into that now, but definitely go check that out. I'll have a link below. So after placement, you need to run your processing channels to them. So you're going to have 2 separate outputs from your console. The first, run an XLR to the outer subs and either daisy chain them, or you can run 3 total and the outer 2 get the same processing. And the center one is going to be the one where we're going to add delay and a polarity inversion. Okay, and then third, place your measurement microphone 6 feet behind the array. So this is where that rearward flipped around center sub is facing. And then we're going to solo our front subs and capture that trace. You do not have to have a delay offset since it's hard really to find the peak of an impulse response in low frequencies. But what I like to do is to get my phase trace flat at the crossover frequency, which in this case is 100 hertz. And so I ended up adding 20 milliseconds of delay just so my phase trace wasn't looking quite so wonky. So anyway, capture that front 2 set of subs at the rear 6 feet behind and store it. And then you're going to now solo your rear sub and look at that trace, and you're going to see that it's going to be ahead. And so it's going to be to the right of that phase trace. And then we're going to slowly add delay until we see that phase trace fall and then line up perfectly with that original front sub trace. And usually, depending on the depth of your subs and how long the line is of your subs, that's usually going to be between 2 and 5 milliseconds what's going on. So I think with my array, it ended up being 3.2. We'll talk more about that later, but you're going to make sure those phase traces are perfectly matched. Then lastly, you're going to invert the polarity of that rear sub, either through a switch on the sub itself or on the output processing from your console or DSP. And you should both see and hear that you have a significant cancellation and dip in energy at the rear of the array, and you're going to have a summation or increase in the amount of SPL at the front of the array. It's still not going to have the total SPL capability of having 3 subs right together with no processing, but you're going to have a much better coverage pattern, and that's a trade-off I will definitely take. So those are the 5 steps of designing and deploying this array. Now let's jump into how does this array actually work. So with this particular gradient inverted configuration, we're adding a distance offset, electronic delay, and polarity inversion to make our cardioid pattern work. So anytime we have 2 signals separated in time, we're going to have phase offset. So I want to talk a little bit about phase and what's happening there. And that is only in regards, and it's going to be different to each frequency in the respective coverage. So low frequencies and subs are much longer in wavelength, so it's going to take more displacement to start to wreak havoc on it. But let's establish some ground rules and how phase is going to work for us, and we'll move forward. So I've got Merlin Van Veen's phase wheel right here, and I can look at the very top that if 2 signals are completely correlated, aka at 0 degrees and are the same signal, we're going to get plus 6 dB. So if of summation. So if I have 0 degrees phase offset, I can look at this A and B wave. The B wave is blue and covering up the A1 because they're perfectly aligned. But I see my red output is a doubling. It goes from 1 here up to 2. So what about if I do a 90-degree phase offset? This is the same thing as moving a quarter way around the phase wheel, either direction. And now I can see that we have 2 waves here that were at 1, and now they can go up to a 40% increase, aka a 3 dB increase. And so even if I have that much offset in time, I can still get summation. Granted, for a 1K wave, that's only a 1 millisecond wavelength and only a 1.13 foot offset. So that's only 6 inches offset for us to move into complete cancellation. And so that would not be good. So if we went further around to 120, that still gives us a stalemate. So we do not have any cancellation. We just don't have any summation either. So what that tells us is if we have a full 240-degree phase range to be able to get some sort of summation, those are our boundaries here. So if we go beyond that, is when we start to get cancellation. So our goal with this array is to get the 2 front-facing subs and the rear one to align in the back and completely cancel out, aka land at 180 degrees offset at our center frequency in the sub. And then the front of the array, everything be between a 240-degree phase span throughout the sub range. So let's put that together here. So I have a Reaper session in which I have 3 different plugins here that are simulating each of the delay offsets, the polarity inversion, the distance offsets, electronic delay, and polarity inversion to make this all happen. And so we are going to use these 2 test signals of our measurement, so this is the front of the array is what we're going to be looking at, and then our reference. So we're applying this processing to the rear sub and going to see what happens to it when it's compared to its original. And then the measurement plus reference is us taking these 2 signals and looking at the final output of that as if we were standing in front of the array. So we can see over here in Smart, these are the 2 transfer functions. We're primarily going to be looking at the orange one. And then once we step through how it works, we'll actually look at the phase traces and results that I captured in Smart when deploying this array. So let's go through one step at a time. So we would need to simulate our physical displacement by adding an amount of delay. And so this is the actual difference in time from the front subs actually coming around to the rear and the rear sub to the back. So I'm going to pick something that was close to what I got in the field, and that was 3.68 milliseconds. So now let's look at our phase traces in Smart. So I can see in our impulse response. So I can see here at our impulse response, I have 0 is our reference. So this would be the original. And then I have that delay offset at 3.68. And that is going to get us a 180 degree phase offset at 136 Hertz. And we can see that here reflected in the magnitude response. So why that particular frequency? So if I go over here to my comb filter calculator, you can see that we have 3.68 milliseconds of time offset between two signals. And that is going to tell me that the single period, or the frequency that perfectly corresponds with making one full trip around the phase wheel, one full cycle, is 272 Hertz. So we're actually going to get summation, or a peak there at that filter, because it's getting its own cycle again at that same frequency. But we're going to see a dip at half of that frequency. And why is that? Since lower frequencies since it's inversely proportional to time, they're going to take longer. So the lower we're going frequency, the longer it's going to take to complete a trip around the phase wheel. So if it's half the frequency, that means it's taking double the time to do it, which means if we have that amount of time offset is only halfway around the phase wheel. And remember, we knew that a 180 degree phase offset would get us cancellation. So that means that frequency, 136 Hertz, is now canceling. So right now we're not done with the array, but know that by adding displacement, that is what's happening to our response, is that we have summation until the time offset grows so much that at that frequency we're getting cancellation. So let's keep stepping through it. Now let's add an electronic delay, or what we would do to add even more to the rear and creating a further displacement. So if we're doubling the amount of delay now, we can expect that cancellation to move further down in frequency. So yes, our impulse response has moved farther away. We now have more cancellation happening here and here. So now let's look at our total time offset, and that's 3.68 times 2. And that's 7.36. If I put that in my calculator now, 7.36, I can now expect my dip to be at 60 Hertz and my peak at 136. And I can verify that here in Smart, that 68 Hertz, we're getting a dip and a dip. So things aren't looking great at the moment right in front. Why do we have a big dip in our frequency response, but we still have our one more step? And since it's a polarity inversion, let's see what happens to everything that's already 180 degrees offset. So we'll go back here into Reaper and add that, our polarity inversion, and wham bam. We have what was at 68 Hertz, our maximum point of summation. And then we have above that. Again, our subrange is only going to be from about here and below is what I'm really concerned with, but that is a bunch of summation right here through 31 Hertz all the way up to the top of our range at 110 Hertz. And I can also verify here that we have our original impulse response at time 0, and then it's coming again later at 7.36, and it is now out. It is reversed in polarity, therefore impulse response is down. So all this data in front of me is verifying that we did these steps right, and I can see that we have summation throughout this range. Okay, we've seen what happens when we do this step by step with test signals. So now let's look at the data I actually got in the field. So I'll turn off these measurements now. If I soloed the front sub, here is my phase trace, and now we finally get to why I ended up picking 68 Hertz as the center frequency, because I saw here when I just took a solar measurement, but that was the middle of the response, and I knew I could get up to 120 degrees phase offset up to the top, and what's close to that is the top of the sub range at 100 hertz. So I knew I was safe. So if I moved up less than 2/3 of an octave, I'm great there. And then longer frequencies are going to be safer and less prone to, or it takes a longer distance offset to make them have any sort of cancellation. And so I knew I was good there. So I'm mainly concerned about the upper range. So 68 hertz ended up being my center frequency. And then I soloed my rear subs. So this is the front subs at the rear. So this is in lower in level since it's having to wrap around the front. And then I went here. This is soloed my rear sub, and I had a microphone in front versus the sub in the rear. So it is closer. And so I'm not surprised to see that measurement at the back is louder. So what I ended up doing, as you can see here, is capturing those front subs at the back, then soloed my front, and then added in the delay. And you can see the phase trace falling until they perfectly aligned. And then I add a polarity inversion, and wham, they cancel. So here is the full array of summation in the front. And then here is the back of the array. And these are microphones 6 feet behind and 6 feet in front of the array. So what I have here on this trace, let's look at my center frequency here. At 68 hertz, that's 5.92 dB above zero. So let's call it 6. And then behind the array at 68 hertz is minus 4.8. So if we round one and not the other, it's about a 10 or 11 dB offset between the two. So I would say 10 or 11 dB is a great place to be as far as cancellation in the rear. That's the same as to our human ears, according to the Fletcher-Munson curve, close to a halving or even a little bit more than that of SPL in the back. And then we get summation in the front, because if we look at our solo of our front subs, and we get a little bump up there. And so that is a trade I'm happy to make, as maybe not quite as much summation in the front as having 3 subs all working together for a lot of rejection in the rear, because here was the solo rear sub and we see that dip down. So that is now 3 subs happening. So 3 times the amount of, or I can add up to 2 more subs for even more SPL, and I'm getting that dip. So I think this was cool to see this array in action. We can also see our coherency in the rear sub way down here, because we're getting our big cancellation. So I think the actual amount of delay was a little bit more than 3.68 in the field, because I can see here that this lack of coherency means we have a big phase offset in the rear. All right, we've covered a lot of ground, some nerdy stuff with phase offsets and delays to all make sure that this subarray covers well in your audience. Make sure and practice this ahead of time. Get MapXT or Map3D or any prediction software that enables you to add processing to the speakers and see what this looks like. Use my Audio Math Survival spreadsheet and plug in these numbers to help get these ahead of time. Run test signals into Smart and compare these measurements. All this will make sure your head's wrapped around what's happening here, so you can get this array sounding great in the field. Don't forget to get the Audio Math Survival spreadsheet at producedbymkc.com/audio toolkit. There's other great stuff in there too. Let me know how you like this video below. Give me a like and watch out for more tutorials and fancy sub arrays.